Okay, just a quick follow-up for the correlation, simple linear correlation, and the simple linear regression videos. Just going to show you really quickly how to do both of those things in SPSS. And so I'll use the exact same data that I used in those videos, in those examples, and it's a very tiny little bit of data, so that it was appropriate for hand computation and for showing all of the steps of a hand computation of these statistics. But I'll just use the same data in SPSS in order to just show you the steps in SPSS, and you can then go back and compare to our hand computations and so forth. So let's just start very quickly with the correlation. To get to correlation in SPSS, assuming that you've already got your data open and entered, we're going to go up here to Analyze, Correlate, Bivariate. Bivariate just means two variables at a time. Let's see, and it popped up on my other screen. There it is. So there's your dialog for these two variables. I'm just going to throw both variables in to the variables list of what I want to correlate. And then I'm going to hit paste. Remember, you could click OK and it will give you your correlation, but you want to get into the habit of always saving your syntax, SPSS syntax, so that you have that as a record of what you've done. It's not very important with such a trivial example as this one, but it could be very important if you're doing a 200 or 300 step analysis, an analysis that needs to be repeated, daily or weekly or whatever, or an analysis that you just need to come back to 6 months from now when you've already forgotten everything that you did. So a good idea to get into the habit of generating SPSS syntax and then saving that syntax. All right, so I've got my syntax. I'm going to click this run, and now the output pops up, and you can see here the correlation, and that pretty much matches what we got by hand. You also see here the p-value, which SPSS labels sig, and occasionally it labels it sig and specifies for you that it's two-tailed. When it doesn't specify that, it's still two-tailed. SPSS reports two-tailed p-values. So you've got your correlation, your p-value, and you also may remember from the t video that I mentioned that correlations, the significance of correlations are actually tested with t-tests. So this is actually a p-value for a t-test, but SPSS doesn't show you that t-statistic. It just gives you the p-value, and you can associate it with this r. And then it gives you the n, which of course for our example is ridiculously small. Another thing, a few things to point out about this, about the SPSS output for correlation. One, this whole thing right here, this table, is called the correlation matrix, and you can do more than two variables at a time, but it's just going to correlate each pair of variables and print it out in a matrix like this. This part of the matrix right here, these entries right here, this is the correlation of a variable with itself, which of course is always 1, and we call that the diagonal of the correlation matrix. And then we call this the lower half of the matrix and the upper half of the matrix, the half below the diagonal and the half above the diagonal. And this half below the diagonal, of course, in our case, it only has a single correlation in it because we only correlated two variables, so we only have one paired correlation. But in bigger correlation matrices, you'll have as many pairs as you have. Well, there's an equation to figure it out. It's like, off the top of my head, I don't remember. But anyway, it's you'll have the number of correlations that you have pairs of variables, and you'll have that in the lower half of the correlation matrix, and you'll also have it in the upper half of the correlation matrix. And you'll notice that the lower half and the upper half are exactly the same. They have the same information in them, and that's because correlation is non-directional. The correlation of x with y is the same as the correlation of y with x. All right, so that's the simple linear correlation. Of course, in this case, this p-value is telling us that our correlation in our example was not statistically significant. So had this been a real analysis, it would pretty much just stop there. Not significant. All right, the simple linear regression. We're going to go to Analyze, Regression, and then Linear. We get the regression dialog here. And in our example, we were actually trying to predict months since car purchase, or the months of car ownership. So we put that in the, SPSS calls it the dependent slot. This is actually the slot for your criterion variable. I think that's the better term unless you have a true experiment, which, you can use regression for true experiments. And then our independent or predictor variables, annual income. All right. And again, we could just go paste and run it, and that would give us the default SPSS output. Let's just do that real quick, and we'll see what SPSS gives us by default. All right, so we click paste, so we have to go back to our syntax and then run this. Okay, and you get out a design matrix that just tells you what your criterion or dependent variable was, what your predictor variable was, and if there were any problems with the model. In this case, there were not. You get a model summary, which I've not talked about yet, but by the time you're watching this, there'll probably be a video up about the goodness of fit statistics for a regression. You have the regression R. This is the correlation between the predicted values and the observed values. And notice how this is always, for simple regression, it's going to be exactly the same strength or amplitude as the simple correlation between the two variables. But this big R, this regression correlation here, is always going to be positive. It will never be negative. It'll just range between 0 and 1. So even though our simple correlation was negative 0.736, our regression R, if you have multiple regression, you would call this the multiple R, is positive 0.736. And then R squared, that's a goodness of fit measure. I'll talk about that in another video, but basically this is interpreted as the proportion of variance in the criterion variable, in our case, months of car ownership, the proportion of variance in the criterion that's accounted for by the predictor or by the predictors in the case of multiple regression. And this is an adjustment for the number of predictors you're using, because the more predictors you use, the higher your R square is going to be just by chance. This adjusts for the chance prediction, basically the modeling of noise or measurement error in your data. And then the standard error of the estimate. This is the expected value of the prediction error that you're going to get, the error of prediction. All right, this ANOVA table, analysis of variance table, is a test of the overall significance of the model. You can see here that our model is not, in fact, statistically significant, not surprising in such a tiny, made-up, wacky example meant mainly to illustrate hand computation. You also notice something, that p-value, 0.156, exactly equal to the p-value of the simple linear correlation between these two variables. All right, but anyway, this overall model, a test of the statistical significance of the overall model. And then down here, the coefficients in the constant slot, it's under in the B column. SPSS labels this column B, but this is actually in our regression model, y equals a plus b x. This is the A. This is the y-intercept right here. And there you have the slope. This is our B in our simple regression equation. You get some other statistics about those, the standard error of those estimates. The beta, that's just the slope in standardized units, so z-score units. And it's actually the slope that you would get. This number and this number would be exactly the same if you translated everything first, if you transformed everything first into z-scores. Then these two numbers would actually be exactly the same. So if you were regressing z-scores of months of ownership on z-scores of income, then these two numbers would actually be the same. And then you get a t-test of the statistical significance of both the y-intercept and the slope of the regression. This y-intercept test is usually not very interesting, because all it's telling us is that the y-intercept is different from 0. In this case, since it's positive, it's telling us that the y-intercept was greater than 0. And that's usually a pretty trivial hypothesis to test. But here, this one is testing this significance of the slope of the regression line. And once again, in the case of a simple regression, you'll notice that that p-value is exactly equal to the p-value of the overall model, which is exactly equal to the p-value of the correlation. And that's always going to be the case in a simple regression. Now, in multiple regression, things get a lot more complicated. All right. So those are the default things. You can also ask for a lot of special things in SPSS, and now's, I guess, as good a time as any to talk about some of those things. So back to Analyze, Regression Linear. It's still set up from what we just did. There's a few things you can save in SPSS. You can save predicted values. You can save them unstandardized, standardized, adjusted, standard error of the mean predictions. You can save residuals in a bunch of different forms here. You can see unstandardized. This is in the units that you measured. Standardized. This is in z-score units. Studentized, deleted, and studentized, deleted. I'll do videos on what all that means some other time. I don't want to make this one go on too long. Some measures of leverage and influence, prediction intervals, and so on. So you have all those options of things that you can save, and if you save them, here, let's just save the unstandardized predicted values. Why not? Because when you save them, I'll show you then where they go. They go into your data set. You can also look at some plots. This keeps popping up on my main screen instead of on the screen that I'm actually recording. So you can create plots of things like your predicted values in z-score format or z-score units versus your actual observed values, the dependent variable, and so on. So let's give ourselves a plot. Why not? You can also do a normal probability plot and a histogram to look at to do some model evaluation, whether your model is a good model or not. You've got some let's see, other options here. These are options for stepwise or backward or forward regressions. I haven't talked about any of that stuff. You don't need to know any of that stuff. Exclude cases. How you want to exclude cases. The default is listwise. That just basically means if there's any missing data, that subject is taken out of the model entirely. All right, I've never really played with style because I don't actually use SPSS output for anything other than looking at myself. I never try to actually report. I never try to use SPSS output in like a table in the paper. I always go through some intermediate step like Excel or something to make it look nice first. So I've never actually played with style here. I don't even know what it does. All right, it doesn't matter. So let's paste and just run that. And so I can show you just basically, we can see that plot. You can see the couple of plots that we asked for, and also I can show you where it saves the predicted values that we just asked for. So we're going to run that. The regression output, here it is. Regression output is exactly the same as it was before. No difference here except, we asked for residual statistics because we asked for a couple of those residual plots. So we get some additional statistics about our residuals. Here's the plots that we asked for. Again, because we have such a ridiculously small sample, these plots are going to look terrible. Normal probability plots, I'll do a video where I talk about these things and how they're used to evaluate the model and whether the model is really a good model or not. Here's the predicted value against the actual observed value, and you can see here that not bad. Okay, so now let me go back to the data, and now you can see in our data that we have a new variable here called pre1, and that's our predicted values. And you can see that actually, if you go back to the video where we did this by hand, you can see that these match our hand computations exactly. So this is exactly what we had predicted by hand. So there you go. All right, I am going to cut it there.